Welcome to this training program on the IBM Selectric Typewriter. This program has been prepared with a specific objective, enabling the business machine technician to study the IBM Selectric Typewriter without the aid of outside help. This is only possible if the instructions given in this program are followed exactly. Failure to heed this may force you to seek skilled help after all. It is absolutely necessary that you know how to operate the IBM Selectric Typewriter. No attempt is being made here to teach you how to use the machine. This portion of the program is entitled Positive Power in the Selectric Typewriter. During the presentation, we will cover theory of operation, exploratory disassembly, assembly, and adjustments. The successful conclusion of this program hinges on your ability to follow instructions and on correctly answering test questions dealing with the covered material and with troubleshooting. This program also assumes that you have an understanding of basic mechanics for office machine technicians. You can familiarize yourself with that material through a training package similar to this one, entitled Fundamentals of Mechanics. This program is the first of a series which presents the IBM Selectric Typewriter in a sequence you can effectively use for the routine checking or inspecting of the machine. This means that after the course, you will be able to use the same sequence of steps when you work on the machine. For this program, you will need at least a Selectric I typewriter. The features and changes incorporated in the Selectric II machine are covered in the fifth segment of this series. The Platen size and pitch of the machine you intend to use are immaterial. You may use an 11-inch, a 13-inch, or a 15-inch Platen machine. We will primarily use a Selectric I with a 13-inch Platen for our demonstrations. To avoid any confusion during our explanations, let us agree that in this picture we are pointing at the front of the machine. The portion of the machine in which the Platen is located will be called the rear of the machine. The part of the machine which is in contact with the table we will call the bottom of the machine. No matter what position the typewriter may be in, whether it stands on its back or on its feet, we will adhere to these definitions. That way, you will always know what front, back, top, bottom, left, and right mean when we use these terms during the program. Feel free to pause the video whenever you need to write something down, which we highly recommend since it helps us remember things, to take more time inspecting a mechanism on your machine, or simply to carry out the given instructions. The decision of when to pause is left up to you. We hope that you will enjoy this program. I'll step you through the cover removal procedure, and we will examine each step more or less carefully. You will be expected to reinstall the covers without any further explanations from this program, so be sure to examine each step as you go. To enable us to remove the covers of the machine, we first have to remove the Platen. Resting against the Platen is the paper bale, which you should pull toward the front, away from the Platen. On both sides of the machine, locate these Platen hold-down latches. Using both thumbs simultaneously, press down on the Platen hold-down latches. While thumb pressure is being applied to each latch, your other fingers lift the Platen by the Platen knob. Whenever you store the Platen, make very sure that it is in a position from which it cannot roll off by itself. Should the Platen ever fall from the bench, a broken knob or a bent shaft is almost certain to be the result. This can easily be avoided with a precaution, such as placing the Platen in a tray, as shown here. Just inside the center section of the machine case, on both sides of the center section, you find these latches. On recent machines, these latches are very short, and you need a screwdriver in order to get at them. Pull them toward the front of the machine. This will unlatch the center section from the bottom cover. If your machine is a very old machine, it may not have this kind of latch at all. If yours is one of those machines, we will discuss the old-style covers shortly. Let us first continue with our examination of the covers that have latches like these. Before we can remove the narrow-lease center section from the machine, it is necessary to rotate the carrier position indicator, or pointer, upward. If you are using a Selectric II, you may simply pull this pointer out of its socket. But if you do, be sure to store it carefully, since it is easily lost because it is transparent and small. You can also rotate up both of the margin set levers. If they do not stay or detent in the upward position, that is okay. Later, when you reinstall the covers, you will just have to be a bit more careful with them and lift them out of the way. It should now be possible for you to remove the center section as shown. Now let us take a few minutes to examine some details about the covers. Notice this stud on the bottom section. On the just removed center section, you will find a matching hole for each of these studs. These are how the bottom cover and center section fit and stay together when the typewriter is being used. When you pull the center section latches toward the front of the machine, this is one of the points on the bottom cover from which they disengage. Also, take a quick look at the latch on the center section so you understand how the covers are locked together. You may even consider practicing the reinstallation of the covers a few times before we continue. The top cover does not have the same type of levers, nor the carrier position indicator. Remove the top cover, or lid, and be sure to store it away from your immediate working area to prevent it from inadvertently being scratched or otherwise damaged. Since we are now ready to lift the machine out of its case, let us remove the paper deflector, popularly known as the paper pan. If your machine is an older machine, the feed rolls will come out very easily, simply by lifting one or both ends out of the feed roll supporting arms. If this is your case, remove the feed rolls as well. On later machines, the feed rolls no longer come out that easily, and it would be perfectly all right for you to leave them in the machine for the time being. However, if you must take them out, you can simply pry one of the arms a bit and then remove them. Be very careful, however, not to force them, so you do not break off the small ends of the feed roll shafts while doing this. Once you remove the feed rolls on the new style machine, if you wish to move the carrier while working on the machine, you should use rubber bands or some tape to prevent the feed roll support arms from interfering with the movement of the carrier. Now turn to the rear of the machine and remove the plastic vent grill from the bottom of the machine by lifting it out of the guide slots. It is your option to leave it dangling on the cord or to remove it completely. Next, turn to the front left bottom of the machine, locate this lockdown lever, and pull it toward the front of the machine. This frees the bottom cover from the frame of the machine so we can separate the two. But before you lift the machine up, please watch the next two steps. In order not to strain a number of relatively fragile parts built around the machine, we first position our left hand under the front left frame of the keyboard, as shown here. Then place your right hand under the A-frame, as shown. With this, you can now lift the machine out of the bottom cover. If your machine is somewhat older, you might find that it does not have this A-frame. It will have various shafts running from left to right instead. It is okay to lift the machine out of the bottom frame only after you have made sure that the shafts by which you want to lift it are properly secured. But even then, be very careful because the shafts can come off in the process. Once the machine is completely out of the case, we should lift it by holding it by its power frame, which is the solid cast frame visible below the right hand. At this point, go ahead and lift your typewriter out of the case. If you tilt the machine on its back, you will be able to examine the slotted lever, which is used to hold together the bottom cover and the machine frame. The slot visible through the hole, indicated by the pencil, fits around a grooved stud on the bottom cover or case. As mentioned, on earlier machines you might find a different kind of cover latch. You will find that the bottom cover is simply pulled off the rest of the machine. After you pull the bottom away from the rest of the typewriter, you can see that the bottom cover is held in place by spring clamps, such as this one. These clamps simply hold onto studs located on the center section of the covers. On this earlier style of covers, the typewriter is literally suspended on rubber studs, which are mounted on the center section. The objective of this feature is to reduce the noise the typewriter produces when it is in use. By loosening the indicated screw, we find that we can easily unlatch the center section from the typewriter frame. It is not necessary to remove the screw completely. Just loosening it so the latch can be rotated will solve the problem. Be sure to check whether your machine comes with these service feet under the power frame. If not, you can order the feet from IBM Corporation under part number 1,174,008. Install them as shown here under the power frame of the machine. These feet will allow you to slide the machine over a smooth surface, such as Formica, without scratching or otherwise damaging the surface. While you are at it, be sure to order these booklets if you do not already have them. You are expected to use these throughout the training program and beyond while working in the field. You will find detailed and easy-to-understand instructions for parts ordering at the beginning of each of these booklets, so there is no need for us to discuss their usage here. Our first subject will be the positive power section of the machine. It consists of the motor, belt, gears, and clutches used in the Selectric typewriter. The study of this positive power section of the Selectric typewriter is equivalent to studying the power roll drive and cams on conventional type bar machines. For troubleshooting purposes, it is of utmost importance that we be able to divide the machine into sections, and that we be able to mentally and practically keep these sections separated while working on the machine. In fact, if we are able to do this intelligently, we can at all times substantially narrow down the overall area or machine section in which we search for a given problem. The second training program will concern itself with the deployment of the force stored in the mainspring. It involves mechanisms such as the escapement for printing operations, the escapement for the spacebar operation, and the tabulation. At the end of this segment, we will also study the backspace, the express backspace, and the carrier return mechanisms, because these mechanisms are used to restore the mainspring tension. In other words, these mechanisms replenish our source of negative power. The third segment of our study is the input section. The most important parts of the input section are the keyboard, the interposers, and the selector latches. Aside from these major parts, the input section only contains a few locks and interlocks. Whenever we wish to perform any function on the IBM Selectric typewriter, we start out with two distinct steps. 1. The selection or choosing of selector latches, which are connected to the mechanisms representing the various functions of the typewriter. And 2. The selection of a power source to operate the selected latches or mechanisms. The name Selectric is a very appropriate designation for this typewriter, since it first selects latches and then drives or operates them electrically. Everything that concerns selection is covered in this input section. Around the source of positive and the source of negative power, we find the output section of the machine. It represents the fourth step in our study of the IBM Selectric typewriter. For output, we will describe the indexing, tilt, shift, and rotate, and printing mechanisms. Segment number 5 is the final part of our study. In it, we will cover the ribbon mechanisms and the correcting tape mechanism. Special features, such as the dual pitch feature of the Selectric II, are also covered in this segment. To perform the following steps of exploratory disassembly, you need a standard office machine repair toolkit, plus a few tools specially designed for the IBM Selectric typewriter. Some of these, such as the hand cycle wheel and the hooverometer on the right, you will already need in this segment of our Selectric training program. A spring hook and a set of Bristol wrenches are also essential. Be sure to obtain these items before continuing. Other special tools will be introduced as they are needed. Now let us install the cycle wheel by turning it top towards the front of the machine. It is most important that the wheel be rotated only top towards the front of the machine. It is very easy to damage the input section or the keyboard by turning the hand cycle wheel in the wrong direction. Turn the cycle wheel only in the indicated direction at all times. If you ever want to remove the hand cycle wheel, first turn it into a position where you can hold the torque limiter with your left hand to prevent it from turning top to the rear. Only then should you apply the torque needed to unscrew the hand cycle wheel by turning it top to the rear. Now move the left margin stop all the way to the extreme left position by first pressing in on the lever, and then sliding the margin stop to the left end of the margin rack. Repeat the procedure to move the right margin stop all the way to its extreme right position. Now depress the tab key and then turn the hand cycle knob or wheel top to the front. The carrier should move towards the right as a result. If the carrier stops before reaching the right margin, first release the tab key, then depress it again while continuing to turn the hand cycle wheel. Repeat this process until the carrier reaches the extreme right position. This exposes the left dust shield so that we can remove it. On the left and right side of the shield, we find two small slotted openings. With the aid of a screwdriver placed into the slot, we can apply moderate pressure, which simultaneously pushes the shield upwards and towards the rear of the machine. With this pressure, we can release the shield from the bracket which holds it in place at the front of the machine. We use the same procedure to release the right side of the shield. Pause the video if you need additional time. Now that the left shield is loose or free in the machine, let us show you how to get it out. First, we place our right index finger under the velocity control cable, as shown here. Use the middle finger to lift the shield out of the machine. We also use the left middle finger to hold up the left side of the shield. This has the advantage that both index fingers are kept free, so that we can use them to guide the shield past the somewhat more delicate steel tapes, called the tilt and rotate tapes, at the rear of this cavity. Now we carefully move the left shield slightly towards the right and front of the machine, in order to be able to lift the rear of the shield. At this point, we need to be careful not to use any force, to prevent damaging the tapes. Once we have passed the tilt and rotate tapes, we only have to pass the velocity control cable in order to completely remove the left shield. At this point, pause and follow the procedure we just explained on your own machine. It is also possible to move the shield too far to the front, causing it to lock under the keyboard. Once you have removed the left shield, examine the parts which hold the shield in its position. Now depress the carrier return key and then turn the hand cycle knob until the carrier stops in its extreme left position. This will expose the right dust shield so that we can remove it too. Should this happen to you, make sure that you first free the shield under the tilt and rotate tapes, and then make a new attempt at lifting it past the tapes. As mentioned earlier, use your index fingers to gently guide the tapes out of the way where needed. Before continuing, you should reinstall the left shield and then remove it again as many times as you need, in order to become reasonably proficient at it. On the left side of the right shield, we also find one of these elongated openings for the screwdriver. Again, we apply a bit of rearward and upward pressure to release the left front edge of the shield from the supporting bracket. Notice also the carrier return cord, or cable, barely visible under the shaft called the print shaft. Before we remove the shield, be sure to examine the position of the velocity control cable in the small clamp, or bracket, at the rear of the right shield. Notice also that the cable goes through the opening to the right of the clamp. The dust shield is placed under the cord. Lack of care during dust shield removal can cause the cord to come off its pulley on the left side of the machine. Once you know how the velocity control cable is positioned, use your left hand to bring the left end of the shield slightly towards the front, and then simply pull the shield towards the right a bit. You will notice it come out of the retainer clamp on the right side of the machine. Once you have it out, again examine the clamps which hold the shield in place when it is in the machine, and then reinstall and remove the shield a few times until you are reasonably sure that you can remove and reinstall it without affecting the tapes or the cords. When you are reinstalling the shield, it is important not to pinch or kink the velocity control cable. Make sure that it is positioned in the indicated opening, and then make sure that the left end of it is held down by the hook or clamp in the shield. After this has been done, leave the shield out, and then, keeping your hands out of the machine, turn it on and off a few times. While doing so, take some extra time to examine the results. You should trace the links to the switch, to the motor, and to everything that is caused to idle together with the rotation of the motor. As a first step, we locate the on-off switch at the rear of the machine, or on older models, underneath the keyboard. The motor transmits its torque, or twisting force, towards the front of the machine via this cog belt. The cog belt is a belt with teeth in it. These belts are designed to eliminate slippage on the pulleys. In the center of the machine, we find that the belt drives a substantially larger pulley, called the hub pulley assembly, or the drive pulley. Observe the parts next to the hub pulley assembly. Notice that the shaft to the left of the pulley does not rotate when all you do is turn on the motor. To make it rotate, you should depress a character. When you depress the character, the shaft does indeed rotate. What happened is that we activated the parts indicated in this picture. These parts constitute a clutch, which is used every time the machine prints a key. Notice the character. In spite of the fact that the clutch is really the print clutch, it is called the cycle clutch. Because of this, the hub pulley assembly is often called the cycle clutch pulley. The hub pulley assembly is directly connected to the shaft situated at the right of it. This shaft is called the operational shaft. Every time the hub pulley assembly turns, the operational shaft turns also. You should think of this operational shaft and the hub pulley assembly as the source of positive power in the Selectric typewriter. Or, if you are an old typewriter serviceman, think of it as the power roll of the Selectric typewriter. Here, the red indicator points at the hub pulley assembly, while the yellow indicator points at the operational shaft. When the motor is turned on, the operational shaft turns continuously. We then say that the system is idling. The hub pulley assembly, together with this continuously turning shaft, provides us with the mechanical torque which carries out the majority of our Selectric typewriter functions. The hub pulley assembly and the operational shaft are thus sources of power with which we can do work. Some of the typewriter functions are carried out by spring action, such as the movement of the carrier from left to right. Still other functions are simply manual functions, such as the tabulation stop set and clear functions. To enable us to readily make the distinction between the two kinds of power, we call the power which comes from the motor, the hub pulley, and the operational shaft positive power. Let us discuss this a bit more, to make sure it is clear in your mind so that we may use these terms later in the program. The power that comes from the mainspring of the typewriter is called negative power. By negative power, we mean energy that is stored in a spring and must be released to the mechanism in order to produce work. The negative power of the mainspring is transmitted to the typewriter mechanisms through the indicated shaft, called the escapement shaft. All of the mechanisms that are driven negatively, through spring action, have to be recharged. Simply put, after we have used a certain amount of spring tension to do work, we must restore that spring tension. Restoring the tension, or negative power, in the mainspring is carried out by the backspace and carrier return mechanisms. The mechanism used to release this negative power of the mainspring is called the escapement. More about this will be covered in the training program entitled Negative Power. As mentioned before, we think of positive power when the power supplied to the mechanism comes directly from the motor. When the motor turns, the hub pulley assembly and the operational shaft also turn, becoming the source of positive power in the typewriter. Whenever the operator calls for some operation, he or she wants the machine to perform a job, and the machine in turn makes use of clutches to tap some of this positive power. The operational shaft turns at approximately 7.5 revolutions per second. The objective of this segment of our training program is to study the construction, the operation, and the adjustments of the clutches that tap this positive power. There are only 3 types of clutches used to tap the positive power: the inertia type clutch, the friction type clutch, and the ratchet type clutch. There is only one inertia type clutch, and it is mounted directly on the motor shaft. All of the friction type clutches use springs to make the mechanical connection between the operational shaft and the driven mechanism. The ratchet clutches also use springs to engage their pawls with the ratchets. With the exception of only one of the friction clutches that use springs, all we need to do to cause a clutch engagement is to release the springs, because at rest, when not in use, they are kept distended or opened. When these springs collapse, they lock the operational shaft to the driven mechanisms. We will refer to these clutches as collapsing spring clutches. In the case of just one clutch, the carrier return clutch, we must cause the spring to collapse in order to make the mechanical connection between the driving operational shaft and the driven parts of the machine. As a result, we call it a collapsible spring clutch. Below the red line, we have named the clutches by the mechanisms they drive. The carrier return mechanism, for instance, is the only mechanism that uses the collapsible spring type of clutch. We will now study these clutches separately and explain how they operate, starting with the motor clutch. As we turn the motor on and off, we observe that the motor pulley can turn, or idle, freely on the motor shaft. The reverse is also true. When the motor is turned on, it is possible to rotate the motor shaft without driving the motor pulley, because the motor shaft and the pulley are not locked onto each other. This motor clutch has been incorporated into the machine to allow the motor to approach normal operating speed before it engages with the motor pulley. This way, the motor has a chance to first develop enough torque to be able to drive the heavier mechanisms of the typewriter. Right next to the motor pulley, we find the clutch hub plate, which holds two clutch pawls. The pencil is pointing at the pivot point of one of these pawls. Notice that this plate is solidly mounted on the motor shaft with set screws. At the end opposite the mounting stud, we find this metallic mass, permanently mounted onto the pawl. At the tip of the pawl, below the pencil, we find a spring, which tends to pivot the pawl clockwise so that the indicated mass is constantly pulled toward the center of the shaft. To understand how the motor clutch operates, we should remind ourselves of a basic principle of motion. When a body is in motion, it tends to continue its motion in a straight line unless it is acted upon by some external force. At the exact point in time when the motor is turned on, the torque of this shaded pole motor is 0. We will study more about the motor a bit later. It takes quite a bit of time for this kind of motor to reach its operating speed, and it is very important that during this time the motor be completely free to rotate without having to carry out any typewriter function. The motor might stall and actually burn out if it were to get a heavy load during this time period. However, once the motor approaches its operating speed, these masses on the pawls try to continue their motion in a straight line, seemingly away from the center of the shaft, against the action of the spring fastened next to the pawl. This is the purpose of the pawl mass, or weight. Once this happens, the heels of the pawls rotate toward the center, into the path of one of the teeth of the motor pulley, as indicated. While there are 3 teeth on the motor pulley, they are positioned so that only one of these clutch pawls engages with the motor pulley at any one time. Examine this as closely as you can before continuing. We will remove the motor from the typewriter. Unplug the machine. Under no circumstances should you continue without unplugging the machine. Most of the procedures proposed in this training program represent just one way of doing things. You might find or develop some other way of accomplishing the same job and feel more comfortable with it, whether because it seems to be a shorter way or simply because you like it better. Consider yourself encouraged to follow your own inclinations whenever they lead you to the desired results on the typewriter. The only restraint is that in disassembling any mechanism, you should never attempt, on your own, to go beyond the limits of your ability to properly reassemble the mechanism you decide to take apart. At times, you may find that your machine has parts that are slightly different from those shown here. When the difference is minor, we may not even mention it. It is then left up to you to analyze the variation in construction of such a mechanism, and you will have to rely on your own ability to analyze and trace mechanisms. Our first step in removing the motor is to remove the belt from the motor pulley. Notice, however, that we will have to move the belt over the washer and the clamp located at the end of the motor shaft, and that this is not so easy because the belt does not have sufficient slack to allow us to do that. We could, of course, remove the clamp and the washer at the end of the motor shaft. A reasonable alternative is to first create the slack needed for the belt removal. With the aid of a screwdriver, we can easily slide the belt toward the left and push it into the space between the hub pulley assembly and the bracket located to the left of the hub pulley. Go ahead and do this on your own machine now until you get your motor belt into the position shown here. Take as much time as you need. As you can see, once the belt is off the hub pulley assembly, it is very easy to lift it over the washer and the seat clamp at the end of the motor shaft. Go ahead and do the same on your own machine. Motor mounting brackets vary. Some motors are mounted into a solid bracket, so that at least one of these brackets has to be removed first. This is the only way to remove the bracket from the machine in order to allow removal of the motor. As is evident in this picture, this bracket will have to be loosened anyway in order to release the power cord. Notice the 2 indicated clamps. They can be taken off the motor mounting brackets. Remove the clamps only, leaving the position of the brackets undisturbed. That way, we can reinstall the motor knowing that the tension of the belt remains unchanged after reinstallation. It is important to always restore sufficient belt tension, so the belt does not jump any cogs or teeth, even when it has to operate the typewriter under maximum load conditions. Whenever we reinstall a motor, we must try to position the motor to give us maximum belt tension and minimum idling noise. In addition, the angular position of the motor must be such that the belt tracks in the center of both the motor pulley and the hub pulley. Remember, whenever we install a motor, we must position it to obtain maximum belt tension with minimum idling noise. Equally important, the motor belt must track in the center of the two pulleys, the motor pulley and the hub pulley. Without that, the belt will soon become frayed at the edges and eventually need premature replacement. For motors having the clamp-down brackets, use a screwdriver in the manner shown and remove the motor brackets. Take your time if you need it. With the clamps off, the motor can easily be removed from its support bracket. If the motor of your machine was mounted in a manner such as this one, now is the best time to remove the indicated ground wire. On machines that have the on-off switch under the keyboard, it becomes necessary to separate the motor from the machine, leaving the switch behind. In that case, we disconnect the motor wires by either unscrewing the wire nuts or disconnecting the wires from the motor. In this case, we disconnect the motor wires directly at the switch. Notice that this motor does not come equipped with a capacitor or any other kind of electrical component that could help it establish its direction of rotation. This is our physical indication that we are dealing with a shaded pole motor. As mentioned, some machines have their on-off switch at the front, mounted at the bottom right of the keyboard. In this particular case, it comes installed at the rear of the machine, and it is possible to lift it out of the machine together with the motor. If your machine has this kind of switch arrangement, make sure that you do not force or break the indicated fork on the toggle arm when you remove your switch. You should complete the removal of the motor, the power cord, the on-off switch, and the ground wire from your typewriter. This represents the typical wiring diagram for the insulated shaded pole motor. With the exception of the ground wire, which is colored green and yellow, or simply green, we can reconnect the shaded pole motor directly to our wall outlet without concerning ourselves about the way in which we connect the motor wires. The shaded pole motor will always start to rotate in the correct direction, regardless of the position of the wires. This, of course, makes it extremely easy to reconnect the motor wires. The ground wire is connected directly to the power frame, or chassis, of the typewriter. Shaded pole motors can be constructed to rotate either clockwise or counterclockwise by properly placing the shaded pole coils. Shaded pole motors are single-phase motors that contain divided stator poles. The coils of the shaded poles develop an axis that differs from the axis of the main poles. The voltage in the shaded poles is induced by the flux in the main part of the poles, so the two fields are also out of phase. The distinct axis and the out-of-phase fields interact to produce a distorted overall field that rotates. Thus, it is possible to have an AC motor that knows its direction of rotation without the use of a capacitor. These motors become quite hot when in operation, and it is important to use caution when working with them. Let us now examine the motor clutch for a moment. The motor clutch is designed to allow time for the motor to build up speed when it is first turned on. Shaded pole motors have a very low starting torque, and it is important not to load them down with anything until they have developed the proper torque. For this, we use the motor clutch. Notice the motor clutch pawls and the weights attached to them. The RPM of the motor must first reach a minimum level before the weights attached to the end of the pawls will tend to swing out against the action of the springs connected to the end of the pawls. As a result, one of the heels of the pawls will engage with one of the teeth on the motor pulley. Yellow pencil. Notice that only one pawl can engage with the motor pulley at one time, the other pawl just rides along. It is most important that the pawl heels be in good shape, showing no signs of wear. Occasional slippage or jumping from one tooth to the next will primarily cause impression problems. Using these special pliers for pressure rings, remove the ring or retainer from the end of the motor shaft, as shown. Be careful not to open the retainer any more than necessary. A pressure ring can easily be broken with these pliers. Once the pressure ring or retainer has been removed, it is easy to take out the motor pulley and find the plastic bushing between the motor shaft and the motor pulley. That is the item in the center with the holes in it. It is very important that the motor be allowed to rotate independently from the motor pulley at the time when the motor is turned on. This condition is needed to allow the motor time to develop the torque required to drive any typewriter mechanisms that might have been tripped while the machine was not plugged in. The motor will simply stall if the initial load is too large for it. When the motor is at rest, the spring indicated by the yellow pencil causes the motor clutch pawl to rest against the lug pointed at by the red pencil. By forming this lug in or out, it is possible to adjust the clearance between the heel of the pawl and the tooth of the motor pulley. This clearance should be kept between 1/4 and 1/2 of 1 millimeter. The springs on the motor clutch must have exactly the correct amount of tension and length to allow proper motor clutch operation. If they are too strong, the rated RPM of the motor will not be sufficient to cause engagement between the motor clutch pawls and the motor pulley, and this can cause premature wear on the heels of the clutch pawls. If the springs are too weak, the RPM of the motor never quite has a chance to build up sufficiently before the clutch pawls engage with the motor pulley, defeating the very purpose of the clutch. It is therefore advisable to replace the whole clutch pawl assembly whenever there is a need to repair the motor clutch. The clutch hub is adjustable sideways on the motor shaft by loosening the set screw. This hub is adjusted in conjunction with the adjustment of the position of the motor. In reinstalling the motor, first, the motor must be positioned front to rear so as to establish maximum belt tension, but without causing the drive mechanism to become noisy. Second, the motor position is adjusted angularly so that the belt runs or tracks on the center of the motor pulley. Third and finally, this motor clutch hub and the pulley are adjusted sideways to allow the belt to track in the center of the large hub pulley. Because different motor belts do not always track in the same manner, it may become necessary to refine one or more of these adjustments after the sequence has been completed. For example, the angular position of the motor may need such a substantial correction that in carrying it out, you develop slack in the motor belt. You may want to review this sequence or even jot it down before moving on. At this point, let us reassemble the motor clutch. Before reinstalling the plastic shim and the pulley, we should lubricate the shaft by applying a film of oil on it. Also, check the motor bearings to make sure they are properly lubricated. When we reinstall the pressure retainer ring, we must be sure to allow some end play for the motor pulley, as shown here. After you have completed the reassembly of the motor clutch, please leave the assembled motor out of the typewriter. As mentioned before, whenever the motor is reinstalled, it must be installed so as to offer maximum tension for the motor belt, but without causing any noise. Immediately to the left of the drive pulley, red pointer, we have a very important friction, or spring, clutch called the cycle clutch. Actually, it is the print clutch, since it is used whenever the typewriter prints a character. The collapsing type clutch spring is located under the indicated part, called the clutch sleeve, so the spring is not readily visible. As mentioned earlier, on the extreme right end of the operational shaft, we have a clutch yellow pointer, which operates in exactly the same way as the cycle clutch or print clutch. It has the added advantage that, in place of a sleeve which completely covers the spring, it has a part called the shift ratchet, which does not cover up the spring. The shift ratchet, however, performs the same functions as those performed by the indicated cycle clutch sleeve. Here we have removed 3 parts of the shift mechanism for easier viewing. Leave the shift clutch on your machine assembled for the time being so you can examine its operation while it is still completely assembled. The name shift mechanism is a carryover from type bar typewriter terminology. In a strict mechanical sense, the Selectric typewriter does not really have a shift mechanism since there isn't anything to shift in the machine. Shift in the Selectric typewriter is only an extension of another mechanism called the rotate mechanism. The shift clutch release arm, or shift clutch latch, indicated by the yellow pencil, rotates counterclockwise and away from the metal lug on the shift ratchet, or shift clutch sleeve. Be sure to confirm this on the fully assembled clutch of your machine. We have called the indicated shift clutch release arm by the name shift clutch latch. You need to know that shift clutch release arm is the name chosen by the manufacturer. Unfortunately, this name is not sufficiently descriptive of the function of this part. When we study the cycle clutch or print clutch, you will find that for the part performing the exact same function, the manufacturer has chosen the name clutch latch. Clutch latch is a much better name than clutch release arm, as you will soon see. For example, A release arm must also be capable of catching the clutch parts before it can release them. We use the name clutch latch rather than release arm. You must, however, be keenly aware of this for the time when you engage in a technical discussion with an IBM-trained person. If we are not sufficiently careful with this, we should be prepared for vehement protest at such a sacrilege on our part. The objective of this program is not to prepare you for a far-out snow job, but rather to make you understand and efficiently repair the IBM Selectric Typewriter. Duplication of nomenclature only delays the achievement of our goals in the area of mechanical comprehension. Throughout most of this program, we will use IBM's nomenclature, and we will make sure that you are properly informed about the IBM nomenclature whenever we deviate from it. Notice that when you depress the Shift key, the indicated shift ratchet rotates top to the front of the machine. This is caused by the collapsing of the shift clutch spring, which originally was held in its expanded state. After releasing the Shift key, you might try to manually rotate the ratchet back into its original position. Notice also that the Shift key comes back up, and how the shift ratchet resumes its latched position so that you can depress the Shift key again. Be sure to allow yourself enough time for these observations. Now depress the Shift lock key. With the aid of a spring hook, you might squeeze the plastic foam dust cover toward the right, between the indicated Shift lock key and the tabulation key. This will enable you to see the latch and the keeper which holds the key down. While you're at it, take a moment or two to trace the mechanical connection between the left-hand Shift key and the right-hand Shift key. The shift ratchet is just like a sleeve which fits over the right end of the shift clutch spring. When we turn the operational shaft with our hand cycle wheel, we provide the torque. The released shift ratchet allows the closing of the shift clutch spring. At its right end, the now collapsed shift clutch spring receives torque from the operational shaft, and as the spring turns with the operational shaft, it transmits this torque, or turning force, to the left end of the clutch spring, where it is connected to the shift cam. The yellow pencil points at the right end of the clutch spring, which is held by the ratchet or sleeve. The red pencil shows the point of connection between the left end of the spring and the cam. It takes a bit of analysis to understand what happens when the rotation of the shift cam is interrupted. Let us go through it once, assuming that the operational shaft is being turned by the power of the motor. Since the shift ratchet in reality is only a sleeve which fits over the right end of the shift clutch spring, when we stop the shift ratchet, we also stop the right end of the shift clutch spring. The shift cam, however, has acquired inertia under the action of the motor, and it continues to turn. The result is that the clutch spring expands and disengages the clutch, or breaks the connection between the operational shaft and the cam. In order to hold the clutch spring in its expanded form, the shift clutch uses the shift cam brake for its small character position and a detent for the capital character position. To simplify this discussion, let us turn to drawings. Notice that another depression of the Shift key on either side of the keyboard releases the Shift lock key. Place the Shift key in its lockdown position. Rotate the hand cycle wheel while observing the Shift clutch. You should have observed that the Shift cam performed only 1/2 of one revolution, and then it stopped. Depress the Shift key again to release the Shift lock. Continued turning of the operational shaft brings the Shift cam back to its rest position. Finally, depress the Shift lock key one more time, then turn the hand cycle wheel until the Shift cam stops again. This is an exploded view of some of the parts which constitute the Shift clutch. The Shift clutch release arm, or latch, as well as the Shift cam brake and detent, were left out. The arbor is fastened to the operational shaft by set screws. Whenever the machine is on, the operational shaft and the arbor turn top to the front of the machine. The arbor is a source of positive driving power for the rotation of the shift cam. On your machine, you will not be able to see the arbor until we disassemble the clutch, because the shift clutch spring is assembled around it and covers it up. In order to transmit this driving power from the arbor to the cam, we use the shift clutch spring. The shift clutch spring is manufactured so that its internal diameter is smaller than the outer diameter of the driving arbor. Notice that the right end of the shift clutch spring is wound top to the front. During a regular shift operation, when the shift ratchet or sleeve is released, the shift clutch spring collapses onto the arbor, which is turning constantly. The friction between the outer surface of the arbor and the inner surface of the shift clutch spring develops a very firm grip, since the spring is as yet stationary and the arbor is turning. The left end of the shift clutch spring is connected permanently to the shift spring retainer plate, and the Platen turn is connected permanently to the shift cam. As the arbor continuously drives the right end of the spring first tightens up very firmly, and then turns with the arbor, ending up turning the retainer plate and the cam along with it. The shift ratchet must turn also, since it is like a sleeve fitted over the right end of the shift clutch spring. As we have seen earlier, we can interrupt the rotation of the ratchet with the shift release arm, or latch. The all-important fact to remember is that the shift clutch release arm, or latch, first interrupts the rotation of the ratchet, and not the shift cam. Not yet, anyway. This amounts to saying that the shift cam continues to rotate because of its inertia. We concluded the previous section by pointing out that the shift clutch ratchet had been stopped by the clutch latch, or clutch release arm, but that the shift cam was still turning because of its inertia. These two conditions, the right end of the shift clutch spring being held top to the rear by the shift clutch release arm, or latch, and the left end of the spring continuing to be turned top to the front by the shift cam, result in an expansion of the diameter of the shift clutch spring. The grip between the arbor and the coils of the shift clutch spring is thus eliminated, so that the arbor can no longer continue to drive the shift cam. Meanwhile, the shift cam still continues to turn because of its inertia. As a matter of fact, somebody had better stop the shift cam from turning too far. The shift cam stop takes care of that. It is mounted directly on the cam. Once the shift ratchet is stopped by the shift clutch release arm, shown by the red pencil, the metal lug on the shift ratchet is always in the path of the shift cam stop, shown by the yellow pencil. Look at it this way. The release arm or clutch latch stops the ratchet, and of course the metal lug on the ratchet. And the metal lug on the ratchet prevents the shift cam from turning too far beyond the point at which the spring clutch is disengaged, and at which the shift cam is in its home position. We will have more about the home position a bit later. It is immaterial which way we stop our shift ratchet, or shift clutch sleeve, whether it is stopped by the inner lug coming to rest against the shift clutch release arm for small character selections, or by the outer, plastic lug coming to rest against the shift clutch release arm for capital letters. The end result is the same. We prevent the shift cam from overthrowing by using the shift cam stop against the inner, metal lug on the shift clutch ratchet. A much more descriptive name for the shift cam stop is shift cam overthrow stop. We strongly recommend that you take your time, whatever time you need, to check on the operation of the shift cam overthrow stop. As you cycle the machine by hand, you will find that the cam does not develop the momentum it needs in order to stop against the lug on the shift ratchet. You should then simply help the cam along by directly turning it with your finger. As a result of your observations, you should have noticed that the shift cam has to overcome the friction of the shift cam brake whenever the shift arm, or cam follower, is in the low portion of the cam. If your typewriter has a recent serial number, you may find that it no longer has a nylon shoe on the shift cam brake. Take another close look at it on your machine, and notice that the brake locks, or holds, the shift cam stationary whenever the operator selects small characters. If you also examine the position of the element, you should find that when the shift cam is held by the brake, the small letters are facing the platen. Now that we know of the existence of this brake, we can say that the rotation of the shift cam is slowed down, or decelerated, by the shift cam brake, and interrupted, or stopped altogether, by the shift cam overthrow stop whenever the shift cam is rotated into the position which selects the printing of small characters. This position of the shift cam is commonly called the lowercase position of the shift cam. The shift clutch spring is used to turn the shift cam into the lowercase position. Once it gets there, the brake is used to keep it there, just like a check pawl would. You should also have noticed that turning the cam into the position from which we select capital characters, commonly referred to as the uppercase position, allows the cam follower, indicated by the yellow pointer, to fall into the dwell of the shift cam, indicated by the red pointer. This cam follower acts like a detent or a check pawl. It simply holds the shift cam in its uppercase position, from which we select capital characters. The shift clutch was used only to drive, or rotate, the shift cam. The cam follower checks, or detents, the shift cam once it has reached the uppercase position. On somewhat older machines, or on heavy-duty machines such as this one here, The shift cam detent might come equipped with a tracking roller to reduce the amount of friction, which has to be overcome by the shift clutch. Let us now disassemble the clutch before we conclude the theory of operation for the shift clutch. First, remove the C-clip at the end of the operational shaft. Be sure to hold your finger in the manner shown in order to prevent the keeper, or C-clip, from flying into somebody's eyes. Then remove the ratchet, or sleeve. And finally, remove the clutch spring. Notice that the clutch spring does not come out willingly. It is simply collapsed onto the shift arbor, and the friction is so great that it is difficult to pull it out straight. However, if you turn the right end of the spring to the rear or clockwise, you will find that it comes off very easily. Can you tell why this is so? Take a moment to formulate your answer. Your answer should have been something like this. The clockwise, or top to the rear, rotation of the right end of the shift clutch spring, without also turning the left end, will tend to open the spring. Specifically, it will increase the internal diameter of the spring, thus making it easy to remove the spring from the shift arbor. Now we have a chance to take a real close look at how the left, or upright, end of the shift clutch spring, shown by the red pencil, is held onto the shift cam retainer plate, indicated by the yellow pencil. Be sure to examine this carefully before continuing. The straight end of the shift clutch spring fits into any one of these openings on the shift ratchet. There is no real need to have this many slots on the shift ratchet. As you will see later, the slots merely increase our adjustment margin, or range. With all of these parts out of the way, it becomes easy to see the brake and the shift cam detent, the cam follower, the brake holding the cam in the lowercase position, and the detent holding the cam in the uppercase position. Now you may wonder why all the fuss about who holds the shift cam in position once it has reached the lowercase or uppercase position. Your question is a very good one. By now you know that the left end of the shift clutch spring is held by the shift cam retainer plate, and that the retainer plate is permanently mounted onto the shift cam. You also know that the right end of the shift clutch spring is held, top to the rear of the machine, by the shift cam release arm, which functions simply like a shift clutch latch, indicated by the green pencil. This latch, or release arm, has the job of stopping the shift ratchet, or for that matter, the right end of the shift clutch spring. It uses the inner lug on the shift clutch ratchet, shown by the yellow pencil, when the shift cam is in the lowercase position, and the outer lug, shown by the red pencil, when the shift cam is in the uppercase position. The only way we can keep the shift clutch spring from constantly driving the shift cam is by holding it expanded or open. And the only way we can hold the spring in an expanded form is by holding both ends of the spring. If we look at the whole operation, we can say that the shift clutch release arm functions like a latch on the right end of the shift clutch spring, and that the shift cam brake and the shift cam detent, the cam follower, function like a check pawl for the left end of the shift clutch spring. Let us repeat this. The shift clutch release arm, or shift clutch latch, holds the right end of the shift clutch spring top to the rear, while the shift cam detent holds the left end of the spring top to the front. Make very sure that you thoroughly understand this explanation. The cycle clutch, or print clutch, used for printing operations, functions in exactly the same manner. Its parts are not nearly as visible as the parts of the shift clutch, and since the same theory is going to be needed again later in this package, you had better review the explanation that accompanies these last two slides. Note that every cam is an example of the simple machine called the inclined plane, which functions like a wedge. The job of the shift cam is to push the shift arm pulley, indicated by the green pencil, out to the right of the machine. On older model typewriters, you will find a backup roller doing the job of the protrusion indicated by the yellow pencil in this frame. The wide portion of the shift cam wedges itself between the backup roller, or this protrusion, and the roller on the shift arm, indicated by the red pencil, whenever the typewriter is to select capital characters. When the shift arm comes from the high portion of the cam to the low portion of the cam, the pressure exerted by the cam follower is such that it can cause the cam to accelerate to an angular speed in excess of the speed of the operational shaft. It is for these occasions that the shift cam brake has been installed. Without the brake, the shift cam overthrow stop would soon break off. Now let us begin the reassembly of the shift clutch. By taking the shift clutch apart as much as we did, we have not broken any of its adjustments thus far. First, let us reinstall the shift clutch spring. Make sure that the vertical extension of the left end of the spring is placed into the corresponding opening on the shift cam retainer plate. In order to slip the spring over the arbor, it is necessary to expand the diameter of the spring. With the aid of a screwdriver, as shown here, this becomes easy. You will be able to guide the left end of the spring to any position you like. Now slip the shift ratchet over the shaft of the hand cycle wheel, and then install the hand cycle wheel. If you then turn the operational shaft, or the arbor, the shift cam always has to turn with it, because the shift clutch spring is collapsed, which amounts to an engaged or closed clutch. After you have experimented with it, turn the hand cycle wheel until the shift cam is in the position shown here. Namely, the uppercase position, with the high portion of the cam under the roller of the shift arm, shown by the yellow pencil, and the shift cam detent in the dwell of the cam, shown by the red pencil. At this point, we are assuming that your shift clutch was properly adjusted before you took it apart. If not, you will learn over the next 2 or 3 slides how to change the position of the spring so as to adjust the clutch. We know that the horizontal extension of the right end of the shift clutch spring fits into one of the slots of the shift ratchet, making the ratchet function just like a sleeve on the end of the spring. The question now is, which one of the slots? And the answer is illustrated here. When the position of the shift cam retainer plate is correct, the right end of the shift clutch spring should line up with any one of the slots of the shift ratchet when you align the center tooth of the outer lug on the shift ratchet, shown by the red pencil, with the transverse tip of the shift clutch release arm indicated by the yellow pencil. What should you do if your machine does not meet these conditions? Here is the answer. You would have to loosen the screws indicated by the green and yellow pencils in order to be able to change the angular position of the retainer plate in either direction, until you meet the conditions described on the previous slide. It is important to mention that you can only rotate the plate counterclockwise by applying counterclockwise torque to the retainer plate. You will be able to turn it clockwise only by applying clockwise torque to the right end of the shift clutch spring, pointed at by the red pencil. Can you explain to yourself why this is so? Try it. Take a moment, and your best bet is to write your answer down on a piece of paper. We rotate the retainer plate counterclockwise, without also rotating the shift cam, because in the counterclockwise direction our torque will tend to open, or widen, the diameter of the shift clutch spring, allowing it to slip over the hub of the shift cam and the shift arbor. In order to rotate the retainer plate clockwise without rotating the shift cam, we must apply the clockwise torque to the right end of the spring, indicated by the red pencil, because this way we will first widen the diameter of the shift clutch spring. When the spring finally slips over the shift arbor and the hub of the shift cam, it will drag the loosened shift cam retainer plate in the clockwise direction. There is yet another way of saying the same thing, explaining why we cannot rotate the retainer plate clockwise without also rotating the shift cam clockwise when we apply clockwise torque to the retainer plate. Clockwise rotation of the left end of the shift clutch spring causes the spring to tighten down on the cam hub and the arbor, thus forcing them to turn also. Whenever the cam rotates with the spring, we are not making any adjustment. For every adjustment, there is one part which is to be considered fixed or stationary. The fixed part constitutes the reference point of our adjustment. The other part is brought to within a specified distance or angle of the fixed part. In our example, the fixed part is the shift clutch release arm with the shift cam in the uppercase position. The part which is being adjusted is the right end of the spring. It is being positioned so that it allows us to engage the shift ratchet in such a manner that the center tooth of the outer, plastic lug lines up with the tip of the shift clutch release arm, or shift clutch latch, as explained on the previous slide. Make very sure that you thoroughly understand this explanation of the shift clutch. In fact, you should not even continue until you can give this explanation in your own words. Notice that the screw indicated by the yellow pointer also holds the shift cam overthrow stop. While you make the adjustment of the angular position of the shift clutch spring, you might as well keep the overthrow stop off the shift cam, particularly if you find that it interferes with the testing of the spring adjustment. Let us now test our adjustment for the angular position of the shift clutch spring. You might consider installing the retainer at the end of the operational shaft, or shift arbor, in order to keep the shift ratchet in its position while you check the adjustment. The checking of our adjustment must be performed in 2 steps. One of the steps is carried out with the machine or the operational shaft being turned manually. The second step requires that the motor and the overthrow stop be installed so that the clutch may be tested under power. In the first part of the test for the angular position of the spring, we measure the amount of power drive of the shift clutch. We slowly rotate the engaged shift clutch from the lowercase to the uppercase position. While we rotate the cam, we keep our eyes on the shift cam detent at the bottom of the shift cam. The condition which we want to achieve is one in which the shift cam is barely driven far enough, or even not quite far enough, to cause the engagement of the detent with the dwell of the shift cam. It may take a bit of additional help, or additional rotation of the cam, for the detent to fall into the dwell which determines the capital letter, or uppercase, position of the shift cam. Under power, this additional rotation is accomplished by the inertia of the cam. In the second part of the test of the angular position of the clutch spring, we also test the action of the shift clutch brake. To perform this test, we need the power of the motor. You might consider making a note that this adjustment should be checked on your machine after the motor has been reinstalled and after the shift clutch has been completely assembled. With the machine turned on, operate the shift key a few times and listen for the presence of a metallic sound whenever the shift cam rotates from the capital character position to the small character position. The shift brake should be adjusted so as to produce a minimum of mechanical clatter when the cam shifts from the capital character to the small character position. Whenever we test any machine on which we have worked, we perform this same test with the shift clutch completely assembled, with the retainer ring and the shift cam overthrow stop. Excessive mechanical clatter would indicate that the shift cam is rotating into the lowercase position with such intensity that the overthrow stop hits against the inner metal lug of the shift clutch ratchet, when the ratchet is already being held by the shift clutch latch, or shift clutch release arm. Once the shift cam stops in the lowercase, or small character, position, it should come to rest with a clearance of approximately 1/2 of 1 millimeter between the shift cam overthrow stop and the metal lug on the shift ratchet. Now for the adjustment of the shift cam overthrow stop. Before you attempt to make this adjustment, you will have to remove the shift clutch ratchet and the hand cycle wheel. Otherwise, you will almost certainly damage the screw head or the ratchet for lack of the proper angle to apply the screwdriver. When the shift cam is in its uppercase or capital character position and the ratchet is manually turned top to the rear, the indicated clearance between the outer lug and the tip of the shift clutch latch or release arm should be at least 1 millimeter. You may have to make the adjustment, then reassemble the clutch and test the result a number of times before you achieve the required clearance. You should, however, always dismantle the clutch before you attempt to change the position of the overthrow stop. With this, we conclude our discussion of the shift clutch. As mentioned, we will use the same theory of operation again to explain the operation of 3 more clutches in the Selectric typewriter. If you said it opens the spring, you nailed it. Turning the right end top to the rear without moving the left end increases the spring's internal diameter, and once that grip on the shift arbor is gone, the spring slides right off. If you said it does not matter which slot, you have it. The right end of the shift clutch spring should line up with any one of the slots on the shift ratchet, so long as the center tooth of the outer lug lines up with the transverse tip of the shift clutch release arm. Here's the trick. Counterclockwise torque on the plate widens the spring, letting it slip over the cam hub and arbor. But clockwise torque on the plate tightens the spring down onto them, dragging the cam along, so you must apply clockwise torque to the right end of the spring, widening it first, and let it carry the loosened plate around. We saw that the motor transmits what we call positive power to the drive, or hub, pulley via the drive belt, and that this torque is transmitted through the direct connection of set screws to the operational shaft, located in the right half of the power frame of our typewriter. When we want to check out any Selectric typewriter, this mechanism must be our first concern, since we cannot operate anything on the machine without sooner or later using this power source. We also saw that the operational shaft turns constantly for as long as the motor remains switched on, and we use clutches to tap that drive. The shift clutch, located at the extreme right end of the operational shaft, was the first such mechanism. Next, from right to left, is a ratchet clutch which operates the cam-marked carrier return index cam. Here we have the old story again. This name is obviously meant to describe the function of the cam, and it was chosen by the manufacturer. We need to be thoroughly acquainted with the name so we can communicate with the manufacturer's representatives, but the merit in learning the name of the part stops there. The same cam, for instance, has an additional function on the Selectric II typewriter, namely to drive the backspace mechanism. Furthermore, this cam does not really return the carrier, as the name seems to imply. The so-called carrier return index, cam, is used to engage the carrier return mechanism. To make a long story short, beware of attaching too great an importance to the name of a given part. The name may imply more, or at times less, than what the part really does. Let's have a short discussion on cams. Consider this drawing of the cam follower, and the operational latch. The cam is nothing more than a wedge which wedges itself between the cam follower and the shaft on which the cam is mounted. Because the shaft is fixed, or stationary, the cam follower has to do the moving. At the point of contact between the cam and the cam follower, we have an oscillation of the cam follower. The amplitude of this oscillation is equal to the distance designated by capital D sub 1 minus the distance designated by the small d sub 2. At the right extreme of the cam follower we obtain, for all practical purposes, a vertical motion designated by m sub v, in spite of the fact that the cam follower has a pivot point and thus rotates. We are only interested in the vertical motion at the right end of the cam follower. We use only mv and simply disregard the horizontal component of this motion. Conclude, then, that the cam and the cam follower are used to convert torque, or twisting force, coming from the operational shaft into linear, or vertical, force at the right end, or the bail, of the cam follower. The Selectric typewriter, for the most part, operates simply by placing hooks or latches under the bail of a cam follower. The latch is then pulled down by the force of mv, and whatever mechanism is attached to the latch is thus made to operate, provided that it is adjusted correctly. One final comment. All the cams on the IBM Selectric typewriter depend, directly or indirectly, upon clutches in order to turn. Thus, whenever we want to perform a function or any operation on the Selectric typewriter, we must select the mechanism. We strongly recommend that you review the text for this slide before continuing, and take some time to find some of these parts in your machine before continuing. From right to left is another ratchet clutch. The cam driven by this clutch is used for the spacebar and backspace mechanisms on the Selectric I typewriters, and for the spacebar mechanism only on the Selectric II typewriters. The next friction clutch is a very simple clutch called the tabulation governor clutch. The gear moves from left to right in a tabulation operation. This spring clutch will restrict the RPM of the tab pinion gear to the RPM of the operational shaft. We will have more about this clutch when we have it out of the machine. This is the carrier return gear. It is a friction spring clutch, but this spring has to be made to collapse, meaning that its internal diameter is larger than that of the arbor when the spring is relaxed. To accomplish this, we use a leaf spring clamp on the left end of the clutch spring, black color, and a nylon shoe on the right end of the spring. Take your time to examine the parts of this collapsible clutch in your machine. The carrier return clutch arbor is mounted freely on the operational shaft without the use of set screws. It receives its torque through a device called the torque limiter. The torque limiter is a friction clutch which works in reverse. It is always closed or engaged so that it constantly tries to drive the carrier return arbor. If, however, the carrier should encounter an obstruction on its way from right to left, such as hairpins, bracelets, or other goodies, This torque limiter clutch must yield and slip over the carrier return arbor before causing injuries to the operator or damaging the typewriter. The red indicator points at the position of the last of our clutches, called the cycle clutch. Actually, the cycle clutch is the print clutch. How many clutches are there in the IBM Selectric Typewriter? Try making a list of those clutches which you can remember. Feel free to use your machine to count them and take a moment to decide. You should have come up with a count of 8 clutches. To further examine the clutches located on the operational shaft, we shall remove the operational shaft from the machine. But before we do, please take a real good look at the depth of engagement between these gears. The black gear is the carrier return pinion, and the white gear is the tabulation cord drum. You will be asked to reinstall these gears so that they engage as deeply as possible with each other, but with absolutely no bind when they turn. It is better to allow for a less than ideal depth of engagement, just to prevent these gears from developing any kind of bind. The same is true of the tabulation governor pinion and the tab drum. With a finger, check the play you have on the pinion gears to develop a feel for this adjustment. By now, you have probably noticed that we occasionally move certain parts out of the way for better picture taking or viewing. This is a time when you might do the same, to obtain easier access to the various parts mounted on the operational shaft. Furthermore, while we work on the operational shaft, we would like no interference with our efforts coming from inadvertently pressing a character key, for example. Fortunately for us, it is very easy to lock out the character keys simply by turning the on-off switch to the off position. Do that now on your machine. In order to free the print shaft, all we have to do is take out this keeper. Out comes the print shaft. You do not need to remove it all the way, since we are only going to work on the right side of the machine. At this point, please go ahead and remove the print shaft from your machine. You will also have to disconnect the escapement link, as shown here. The spring hook is by far the best tool to handle the clevises encountered on so many mechanisms in the Selectric typewriters. In order to prevent the escapement link from losing its adjustment, in other words, to prevent the clevis on the escapement link from turning, it is advisable to connect the clevis to the tabulation cord, as shown here. It can happen quite easily that if a serviceman fails to do this, the escapement link is left hanging down under the operational shaft during reassembly. Usually, this is discovered after the operational shaft is again nicely in its position and properly adjusted. Let us simply say that it is quite cumbersome to remove the escapement link out of this situation without first removing the operational shaft. If you do not want to hook up the link with the tabulation cord, your best bet might be to remove the link from the machine altogether. We will show you how to adjust the link when it comes time to reinstall it. Now remove the shift ratchet and the shift spring, as shown, and leave them right on the shaft of the cycle wheel. Then loosen all of the indicated set screws. If you happen to be working with an 11-inch Platen machine, you will not find the collar indicated by the blue pencil. When choosing the wrench for the set screws, we must make very sure to find the correct tool for the job, as the sockets in the set screws are not always the same. Choosing the wrong wrench, such as an Allen hex wrench instead of a Bristol wrench, will invariably cause problems, such as stripping the set screws or damaging the wrenches. The torque limiter indicated by the red pencil on the left usually has 2 set screws rather than just 1. When you loosen them, be sure to back them out far enough, because they fit into a recess on the operational shaft. Once the collar on the right side of the shaft, pointed at by the blue pencil, is loose, it is possible, at least on the new machines, to move the operational shaft somewhat to the right, but not yet out of the machine. If you happen to be working on a level 1 machine, which is a really old machine, you will not be able to move the shaft to the right yet. On level 1 torque limiter mechanisms, there is a second C-clip, or retainer ring, located on the operational shaft between the carrier return clutch driving arbor and the arbor of the carrier return pinion gear. To be able to see the point at which the 2 arbors come together, it is necessary to spread the coils of the carrier return clutch spring, as we have done here with the aid of a screwdriver. In order to get at the keeper, we must first loosen the set screws of the torque limiter, indicated by the yellow pencil, then move the torque limiter and the carrier return driving arbor towards the left. Only then will we be able to see and get at the second C-clip on the operational shaft. If you happen to be working with one of these old machines, take out the C-clip at this point. How do you know whether or not you have such a C-clip in your machine? Try pulling the operational shaft to the right while holding the carrier return pinion to the left. If the operational shaft moves at all, you already have a later style, and you do not have to worry about the second C-clip. And if you turn out to have one of these oldies, you may leave the C-clip out for good. It was placed there only to aid you with the adjustments. We will show you how to make the adjustment without using the extra C-clip. Thus, after you have it out, you may as well forget it. Regardless of the level of the torque limiter in our machine, we need to be able to move the operational shaft sufficiently to the right in order to remove the indicated C-clip, mounted on the operational shaft to the right of the carrier return pinion gear. This C-clip is a very important part of the operational shaft. It is the only part on the shaft which is not adjustable sideways unless we also move the operational shaft sideways. All other parts can be moved left or right at will because they are only fastened by set screws. The C-clip, however, fits into a groove on the operational shaft, and that is the only groove there is for it. The job of the C-clip is to prevent the carrier return pinion, located to the left of it, from moving to the right. The carrier return pinion must be properly engaged with the tabulation cord drum, as we asked you to check a little while earlier. This amounts to saying that during reinstallation of the operational shaft, we first position the carrier return pinion into proper engagement with the tabulation cord drum, and then we bring the operational shaft, with its C-clip already installed, against the carrier return pinion. The position of the operational shaft, therefore, is adjusted sideways so as to comply with this condition. C-clip against the properly engaged carrier return pinion. The tabulation cord drum, then, is our fix point or reference point for the adjustment of the left to right or right to left position of the operational shaft. Needless to say, then, it is most important that the tabulation cord drum be positioned properly on its shaft, called the escapement shaft. The position of the tabulation cord drum is a fundamental adjustment. Once it has been set, other parts are adjusted in relation to it. The position of the tab drum is just as important as the position of the hole in the power frame. The tabulation cord drum should be positioned in such a manner that the inside surface of the drum is flush with the end of the escapement shaft. However, the escapement shaft must also be positioned and held all the way to the front of the machine, with minimum end play, before there is any point in adjusting the position of the tabulation drum. The C-clip or keeper is simply pushed out with the aid of 2 screwdrivers, as shown. When it comes off the shaft, be careful and prepared to have it jump, since it is quite strong. Because it will jump downwards, the danger of it hitting somebody's eyes is minimized. You should be very careful nevertheless. Pull out the operational shaft until you are able to remove the tabulation governor clutch, as illustrated here. A pair of long tweezers is a very handy tool for this job. If your machine was properly taken care of before you got it, the clutch is completely dry, without any grease or oils. Let us examine the tabulation governor clutch for a moment. The hub in the left hand is really a combination collar and arbor. You know that it was fixed on the operational shaft by the set screw. This means that it must constantly turn top to the front with the rotation of the operational shaft. As you try to turn the collar arbor top to the front, you notice that the clutch spring offers very little or practically no resistance, because this rotation, without also turning the pinion in the right hand, tends to expand the internal diameter of the spring, thus disengaging the clutch. The indicated right end of the spring will be dragging on the arbor of the pinion, causing diameter expansion. This expansion is only enough to overcome the friction of the spring on the pinion arbor. On the older machines, there is not even a clamp holding the left side of the clutch spring. Try it the other way around. Hold the left-hand collar arbor, which IBM simply calls the hub, and do not let it turn. Then, cautiously, try turning the tabulation pinion top to the front without forcing or damaging the spring. You now notice that the spring grips the collar arbor. In fact, if you are not careful, you will notice that the twisting force top to the front applied to the pinion will tend to suck a spring coil in between the 2 arbors. This means that we have to install the pinion and the arbor in such a way as to allow for absolutely the minimum play between them, for the sake of the spring. We do this by adjusting the position of the collar, which is placed to the right of the tabulation pinion. From these observations, we conclude that the tab governor clutch will close if the tabulation pinion turns top to the front while the hub, or collar arbor, remains stationary. The tabulation pinion gear, through friction, will drag the right end of the spring and thus attempt to close it around the pinion gear arbor. If you counted 8, well done. That's every clutch tapping power in the machine, from the inertia clutch on the motor shaft to the friction and ratchet clutches along the operational shaft. If you came up short, it's worth another walk down that shaft before we move on. Here is the test. Pull the operational shaft to the right while holding the carrier return pinion to the left. If the shaft moves at all, you have the later style and there is no second C-clip to worry about. And if you do have one of the old ones, you may leave that C-clip out for good. It was only ever there to help you with the adjustments. Since the operational shaft is constantly turning, the hub has to turn also, while the tabulation governor pinion can only turn if the tab cord drum turns. This occurs during spacing and during tabulation. In fact, during tabulation, the tabulation governor pinion will try to turn top to the front faster than the operational shaft. That is when the tab governor clutch comes in. It limits the RPM of the tab pinion gear to the RPM of the operational shaft, giving us an even and smooth movement of the carrier from left to right during tabulation. As a matter of fact, when the machine is reassembled again, you might depress the tab key and then observe that the carrier will only move from left to right by the distance needed to tighten the tab. If you then, with a screwdriver, push the right end of the governor clutch spring top to the rear, as shown here, the carrier will take off immediately, and if you aren't careful, it will knock the screwdriver right out of your hand. You had better use your left hand to prevent the carrier from causing any mishap. Now remove the carrier return clutch assembly or the torque limiter assembly. We shall examine it a bit later. The next item out in our disassembly routine is the operational cam assembly. The operational cam assembly is made up of 2 ratchet clutches, each one with its own cam. The cam on the left is the spacebar cam, while the cam on the right is used for indexing, carrier return, and, on modern machines, the backspace mechanism. On Selectric I models, the backspace mechanism is powered by the spacebar cam. By removing the C-clip, which we are holding in place here with a pair of pliers, it is possible to get a good look at the inside of the double ratchet clutch assembly. Take some more time whenever you need to catch up with the steps presented in the program. You are expected to go through each step on your own machine, so be sure to follow along as closely as you can. First of all, look at the shape of these cams. The spacebar cam on the left is double-lobed, while the index carrier return engagement cam on the right has only one lobe. This means that the spacebar cam causes 2 oscillations of the cam follower for each complete revolution of the cam, while the carrier return engagement cam causes only 1 oscillation of its cam follower. We only need half of 1 revolution of the spacebar cam in order to escape our carrier, and in fact, this is exactly how the machine operates. Half of 1 revolution per operation for the spacebar cam, and 1 complete revolution per operation for the carrier return engagement cam. Whenever the ratchet clutch is released or allowed to engage, it is up to the spring, indicated by the red pencil, to engage the tooth of the clutch pawl, indicated by the blue pencil, with one of the teeth of the clutch ratchet, indicated by the yellow pencil. Since the ratchet is continuously rotating, because it is mounted on the operational shaft, the cam ends up turning also. This is the carrier return engagement cam, seen from its left side. If it were mounted and operating in a machine, it would now be rotating clockwise. The small step on the clutch disc or clutch flange, indicated by the yellow pencil, will eventually meet the clutch latch, which, with respect to the cam, sits in the 6 o'clock position, directly underneath the clutch. At the tip of the clutch pawl, in the 12 o'clock position, you can see the backside of a pin riveted into the pawl. This pin extends into an opening on the clutch disc. When the clutch disc is stopped by the clutch latch, IBM calls it the clutch release lever. The inertia of the cam and the other parts of the clutch keep the cam turning. Since the pawl is fastened to the cam at the point indicated by the red pencil, it continues to turn also. As the cam and the pawl continue to rotate, the pin of the pawl at the red pencil meets the edge of the opening in the clutch disc, with the end effect that the pawl is cammed out of engagement with the ratchet, against the action of the ratchet pawl spring, or simply the ratchet clutch spring. In other words, when the ratchet cam finally stops rotating because the pawl pin reaches the end of the opening in the clutch disc, the spring is stretched. But a spring does not just sit there and remain stretched, it will collapse unless we hold it in its stretched condition. In fact, it would tend to turn the cam top toward the rear of the machine. The point of the cam indicated by the blue pencil would turn to the right in this picture. What we need is to check the stretch spring. On the clutch disc, at the point indicated by the yellow pencil, we apply the clutch latch, or as IBM calls it, the clutch release arm. The clutch latch then prevents the clutch disc from rotating clockwise. On the outside of the operational cam assembly, this engagement between the plastic or nylon check ring and the check pawl prevents the cam from rotating counterclockwise. The two parts, then the clutch latch and the check pawl, keep the spring stretched. You'll recall that exactly the same thing happened with the shift cam. On the right end of the spring, the shift clutch latch or release arm prevented the shift ratchet from rotating clockwise, while the shift cam brake and the shift cam detent did the job of the check pawl, namely, keeping the clutch spring stretched or its diameter enlarged. These are the clutch latches, or clutch release arms, for the operational cam clutches. Now that the ratchet clutch assembly is out, they're very easy to see, but that's not at all the case when the machine is back together. It is very important that you be able to recognize these clutch latches even when the machine is assembled, so take a real good look at them. These are the check pawls for the operational cam clutches. They're easy to see when the machine is assembled because they operate on the outside of the operational cams. This is the best angle for inspecting the operational clutch latches, or release arms. Since they have to stop the clutch disc, and since the discs are right next to the cams, the clutch latches operate very close to the lateral surface of the cams. It is important that they do not rub against the cams, and for that, you need to develop the ability to spot them through this opening, even with the machine fully assembled. Take whatever time you need to locate them through this opening. The two arrows in this drawing point at the places which should be checked for clearance between the clutch latches, or release arms, and the cams. This drawing came out of the Selectric Typewriter Service Manual, form number 24156-15. That manual contains superb illustrations of many otherwise difficult-to-see parts on the Selectric typewriter. The text does not seem to have been written for instructional purposes, and as a result, it appears extremely cumbersome and difficult to the unprepared student. But once basic familiarity with the mechanisms of the typewriter has been developed, it is the most detailed, exact, and useful book for the serviceman, and we recommend that you use it frequently for review purposes. Since the clutch latch and the clutch check pawl act in opposite directions, to rotate the ratchet pawl out of the ratchet and keep the clutch spring stretched, the question arises, where and how do we adjust this clutch? It is done by this eccentric. Since the nylon check ring is held in place by two screws, we must also loosen the other screw before we attempt to adjust the position of the check ring. As you can readily see by the tolerance indicated in this frame of your adjustment and parts manual, the adjustment of the clearance between the pawl and the ratchet is not at all critical. On the one hand, we must make sure the pawl does not drag over the teeth of the ratchet when the operational shaft is turning. On the other hand, we must allow some overthrow play for the cam after it has reached its rest position. The rest position of a clutch is frequently called the check pawl position of that clutch, signifying that the check pawl is engaged with the check ring. It's now time for a bit of review, and we'll take the opportunity to introduce a new part and its function, the interposer. There are many interposers on the IBM Selectric typewriter. The name is very descriptive. An interposer is positioned between the keyboard or the operator and the output mechanism chosen by the operator. Specifically, each interposer has two functions: to select one or more selector latches and to engage a clutch, by which the selector latch or latches can be powered to perform the desired function. We will see later that there are only a few interposers on the Selectric Typewriter which have a bit of a lesser function. Starting at the left side of the drawing, when the key lever is depressed, the key lever pawl is pressed down also. The key lever pawl pushes down on the left, or front, end of the interposer, causing the interposer latch to disengage the latch plate. When the left or front end of the interposer is depressed, the interposer rotates around the screw located at the center or underneath the interposer. After the disengagement of the interposer latch, the interposer spring, located on the right or rear tip of the interposer, causes the interposer to slide toward the rear. This rearward motion places the operational selector latch underneath the bail of the cam follower, in a position where the operational selector latch is ready to receive the downward push from the bail of the cam follower. Notice also that the shorter, lower lug of the interposer will meet the vertical extension of the clutch release lever, which we call the clutch latch. Rearward motion of the interposer, then, causes the clutch latch to rotate counterclockwise, so as to disengage the clutch disc and allow the engagement of the clutch pawl with the operational clutch ratchet. Since the ratchet is continuously turning counterclockwise, the operational cam will also turn counterclockwise. So with the right or rear tip of the interposer, we performed the selection of the operational selector latch. And with the lower lug of the interposer, we caused the ratchet clutch to engage, so we could provide power to the mechanism attached to the operational latch. The rotation of the cam causes the cam follower to oscillate, and in the process, the bail of the cam follower pulls down the operational selector latch. Notice, however, that underneath the cam follower, there is a part called the interposer restoring lever, which is also made to oscillate when the cam follower oscillates. During the clockwise portion of the oscillation of the interposer restoring lever, the interposer is made to latch up again with the interposer latch plate. In the process, the key lever pawl is rotated toward the left, or the front of the machine, in case the operator is still holding the key lever down. This illustration assumes the operator is still holding the key lever down. Therefore, the key lever pawl must be rotated out of the way, which is toward the front of the machine, or the left in this drawing. Notice there is one more step on the key lever pawl, which even now is still over the left, or front, end of the interposer. With the operational controls, it is possible to depress the key lever down into a repeat operation position by applying additional pressure to the key lever. If our operator had done this, the left, or front, tip of the interposer would have been held so low that the interposer latch would be unable to relatch with the interposer latch plate, and we would have had a repeat action for this operation. In this case, the interposer was allowed to relatch with the plate, and this allowed the clutch latch, or clutch release arm, to rotate back into the path of the step on the clutch disc, enabling the clutch latch to stop the continued rotation of the clutch disc. The cam, the pawl, and the check ring assembly, however, continue to rotate under their own inertia, against the action of the pawl spring, thus stretching the spring. After the clutch pawl has been forced out of engagement with the ratchet, the check pawl falls into the opening of the check ring, trapping the spring in its distended condition. The check ring opening is not visible in this drawing because the check ring is located on the far side of the operational cam. Continued rotation of the cam is eventually stopped by the pin in the clutch pawl hitting the outer corner of the opening in the clutch disc. Under the action of the clutch spring or clutch pawl spring, the cam would now turn clockwise if it weren't for the check pawl preventing it. Make sure you can repeat the explanation given for the last two slides on your own. In just a little while, you'll be asked to repeat this explanation while tracing the parts on the machine, rather than on this nice drawing. Now let us trace the components on the machine. After the spacebar key lever and the key lever pawl, we come to the front tip of the spacebar interposer. On this partially disassembled machine, it is easy to spot the interposer latch plate, and for that matter, the interposer latches. Be sure to locate them on your assembled machine. If you follow the interposer indicated by the yellow pencil to the point indicated by the red pencil, you'll be able to locate the operational selector latch for the space bar mechanism. Make it a habit to devote special attention to those areas or parts of the machine which are somewhat more difficult to see. If you have difficulty seeing them during troubleshooting, you'll find you have to make up for it by visualizing their operation. Such visualization is only possible if you are thorough when you study the mechanism, so don't try to cut corners for your own good. Here, the yellow pencil indicates the lug of the interposer, which is responsible for tapping the source of positive power, or simply, the lug responsible for engaging the clutch. The red pencil points at the lower extension of the clutch latch, or the clutch release lever, as IBM calls it. The yellow pencil in this picture shows the lug of the interposer restoring lever, or interposer restoring bridge, which during operation is acted upon by the cam follower. Notice that both sides of the interposer restoring bridge come equipped with this lug. This enables the cam follower of either operational cam to operate the restoring bridge. Do you still remember that the spacebar cam is double-lobed, while the index carrier return engagement cam is single-lobed? When you consider this fact, you realize that the restoring bridge operates at two different speeds, a fast one for spacebar operations and a slow speed for the index carrier return cam operations. At this point, see if you can repeat on your own machine the complete theory of operation for the spacebar mechanism, excluding, of course, the output mechanism, the parts of which are attached to the selector latch. Try to explain how the mechanism works under single-action operations and also how it works under repeat-action operations. Don't continue until you're capable of doing it. If you need to, review the material we covered starting a few slides back before moving on. In either case, we wish you good luck. The spacebar cam is the double-lobed one. And here is what that buys you. The restoring bridge runs at two different speeds, a fast one for spacebar operations and a slower one for the index and carrier return cam operations. The next item out of our machine is this collar. If you're using an 11-inch Platen machine, you do not have the collar shown here. All 13-inch and 17-inch machines, however, do have it. The function of this collar is to prevent the operational shaft from moving toward the right. On 11-inch machines, this function is performed by the operational cam assembly, which is mounted on the operational shaft directly against the right bearing of the shaft. The same is true for the collar shown here. It prevents the operational shaft from working itself out toward the right, and it is mounted directly against the left side of the operational shaft bearing. To prevent the operational shaft from working itself toward the left, we utilize this part. In summary, then, we can say that the operational shaft bearing is responsible for holding the lateral position of the operational shaft. Locate the left side bearing collar for the operational shaft. It fits inside of this hub. During servicing, whenever we have to remove the operational shaft, we should check the amount of play that exists between the operational shaft and the bearing collar, or between the bearing collar and the drive or hub pulley assembly. More often than not, we need to replace the bearing collar. Notice these lugs on the drive or hub pulley assembly. The lugs on the drive or hub pulley assembly fit into these openings. These are the openings of the torque limiter hub. On the standalone, or office products, Selectric Typewriter, the torque limiter hub is made of synthetic material, which has the advantage of reducing noise during the operation of the machine. On older machines, or on input-output models, you will find metal torque limiter hubs. Metallic torque limiter hubs come equipped with nylon inserts for the purpose of noise reduction. These inserts wear and need occasional replacement. This is the torque limiter of an older office products typewriter. As you found out during the disassembly of the operational shaft, the torque limiter hub is anchored directly onto the operational shaft, becoming an integral part of the operational shaft when the machine is fully assembled. Let us now take a closer look at the so-called torque limiter assembly. The torque limiter assembly is made up of two clutches, the carrier return clutch on the right and the torque limiter clutch proper on the left. You've probably noticed by now that the carrier return pinion gear fits quite loosely inside the carrier return clutch spring. This means the clutch spring must be made to collapse or tighten up onto the arbor of the carrier return pinion gear. Notice that on the left side, the carrier return clutch spring is held in place by a clamp, which fits over the spring, holding it to the carrier return driving arbor. That takes care of holding one end of the clutch spring. During carrier return operations, the other end is held by the carrier return shoe, as we will examine when we study the carrier return mechanism. The carrier return clutch, by the way, is another clutch which should be kept free of lubricants. Because any lubricant placed anywhere on this assembly would eventually work its way to the spring clutch, we simply leave the whole assembly dry or free of grease at all times. The large friction spring on the left is the torque limiter clutch spring, or simply the torque limiter spring. This torque limiter clutch spring is the only part which holds the indicated carrier return driving arbor to the torque limiter hub. The job of the torque limiter spring is to control, or limit, the amount of twisting force, torque, that can be transmitted from the torque limiter hub to the carrier return clutch driving arbor. The exact amount of torque delivered by this clutch is determined by the spring tension developed between these two anchor spots for the torque limiter clutch spring. Be very careful not to mar the surface of the carrier return driving arbor with pliers when you perform this experiment. If you hold the carrier return clutch driving arbor stationary with pliers, you can turn the torque limiter hub top to the front and thus feel the amount of torque delivered by the torque limiter hub. The left end of the torque limiter spring is held by the metal bracket at the point indicated by the yellow pencil. For coarse adjustments of the carrier return clutch torque, we can change the position of the bracket by first loosening the screw indicated by the green pencil. For fine adjustments of the carrier return clutch torque, we use the indicated eccentric stud. Notice that it, too, is mounted on the torque limiter hub. You will find that on later machines, this stud no longer exists. Instead, we simply use various spring anchoring points on the bracket, which is used to hold the left and the right end of the torque limiter spring. In conclusion, let us say that the torque is adjusted by the tension of the spring indicated by the green pencil. If we should reach the maximum adjustment for the stud which holds the spring, then we must go to the coarse adjustment of the torque limiter hub. We would thereby change the angular position of the torque limiter spring. We mentioned earlier that the carrier return clutch spring must be made to collapse. We accomplish this by applying a dragging pressure to 2 or 3 of the rightmost coils of the carrier return clutch spring. To fully understand this, it is necessary to consider that the carrier return spring is constantly turning with the torque limiter hub, while the carrier return pinion gear is stationary. The dragging effect upon the carrier return clutch spring is generated by this carrier return shoe. When this shoe presses against these outer coils, the friction developed between the rotating spring and the stationary carrier return pinion gear causes the diameter of the spring to become smaller, until the spring develops a firm grip onto the arbor of the carrier return pinion gear, and until eventually the gear is forced to turn with the spring. The engagement of the carrier return shoe with the carrier return spring is caused by the carrier return engagement cam, which we studied a bit earlier. As we mentioned earlier, the mechanism which accomplishes this engagement is covered in our training package number 25 on the IBM Selectric Typewriter. The turning of the gear top to the front, red pencil, will cause the tabulation cord drum to turn top to the right. This rotation of the tabulation drum gear will feed out the tabulation cord, which is attached to the left side of the carrier. As you follow the escapement shaft to the rear, you find that the carrier return cord drum, red pencil, will also turn top to the right, but it will tend to pull in the carrier return cord. The carrier return cord extends out of the left side of the carrier. When we pull on it at the same time as we feed out the tabulation cord, the end result is carrier movement from right to left, or simply, a carrier return operation. Now it is time to reassemble the operational shaft. We shall first install all the components onto the shaft without tightening them down. As you install the torque limiter, be sure to place the carrier return pinion gear into proper engagement with the tabulation cord drum gear. It is very easy to end up with the pinion gear to the right of the drum gear teeth. This is the order, or the relative position of the parts, in which the various clutches should be installed on the shaft. Take a moment now to reassemble the operational shaft. The last item on the shaft should be the C-clip, or the C-retainer. As we have seen earlier, our first concern goes to the engagement between the carrier return pinion gear and the tab cord drum gear. We want maximum engagement, all right, but we are willing to compromise on that issue, since we definitely do not want any binds between the two gears. Remember also that the C-clip on the operational shaft is responsible for preventing the carrier return pinion from drifting to the right. Furthermore, we remember that the fixed point, or reference point, for this adjustment is the tabulation cord drum. We have already seen that it should be set so that the inner surface of the drum is flush with the front end of the escapement shaft, but that isn't enough. It is also necessary to make sure that the escapement shaft is positioned properly. This means that you should apply finger pressure onto the indicated mainspring hub, which is also the rear end of the escapement shaft, so as to assure that the escapement shaft is positioned all the way forward. This we must do before we can use the tabulation drum as a reference for the carrier return pinion adjustment. From here, we suggest you first watch the rest of this program straight through. Then get yourself a piece of paper, come back to this point, and make notes while we go through the adjustments once more, pausing as many times as you need. Only the third time through should you perform the adjustments, using your own notes as much as possible. The reason for this is that we will first give you the adjustment sequence, and then we will give you some more details about the adjustments. Our objective is simply that after this training package, you must be able to adjust the operational shaft and its clutches. Now let us go through the steps. For the sake of a better understanding, let us pretend that these parts are all that there is to the operational shaft. The first step, by sliding the carrier return pinion gear left and right, we select the best tooth engagement between the pinion gear and the tabulation drum gear. Second step, while holding the carrier return pinion gear in place, we slide the operational shaft leftwards until the C-clip, or the retainer, black pencil, comes to rest against the right side of the carrier return pinion gear. Third step, now we move the shift arbor indicated by the yellow pencil all the way against the shift cam hub, or the right side of the operational shaft bearing. Fourth step, bring the collar indicated by the green pencil all the way against the left side of the operational shaft bearing. Once this has been done, the position of the operational shaft is set, even though the position of the carrier return pinion gear has only been limited at the right side. Fifth step, now we bring the torque limiter hub and the carrier return driving arbor all the way against the left side of the carrier return pinion gear. It is most important that you allow only enough clearance, or end play, for the carrier return pinion gear so that it can rotate freely. The end play must be kept to an absolute minimum. Otherwise, a coil of the clutch spring might be pulled in between the arbors during carrier return operations. Such an occurrence will invariably and permanently damage the clutch spring, forcing you to replace it. In a shop situation, once you know that your adjustment of the position of the operational shaft is correct, because you checked it prior to removing the operational shaft, you do not need to make the adjustment of the shift arbor. All you have to do is simply leave the shift arbor in its place throughout the process of removal and reinstallation of the operational shaft. For the same reasons already pointed out in connection with the carrier return clutch spring, the end play of the operational shaft must be minimized. If we don't minimize it, the shift clutch spring might get sucked into the space between the two arbors indicated by the yellow pencil. Since we have established the position of the operational shaft by the fastening of this shift arbor, we should now only make sure that both of the set screws are properly secured. Whenever you run into a shift arbor with only one set screw, you would do yourself a favor by replacing it with an arbor that has two set screws. Two set screws definitely hold the arbor in place better than just one. In order to minimize the end play of the operational shaft on 13-inch and on 15-inch machines, we would use the collar, or on 11-inch machines, the operational cam assembly. Be sure to hit the flat spots on the shaft before you tighten any screws, because set screws tightened on the round portion of the shaft will mar the shaft to the point where you might encounter difficulty in removing the tightly fit components of the operational shaft. Now let us focus our attention on the torque limiter again. The small bias spring has probably come off your torque limiter clutch with all the handling you have given it. If not, remove it at this point. The yellow pencil is pointing at the approximate position of the separation between the torque limiter hub and the torque limiter arbor. It is very likely that you might push the torque limiter assembly all the way to the right in order to minimize the end play of the carrier return pinion gear, without having minimized the play between the hub and the torque limiter arbor. In order to remove this play, we must know how to use our tools, because the torque limiter spring is quite strong, and it makes it hard to slide the hub or the torque limiter arbor sideways when the spring is on the assembly. First, be sure that both of the set screws of the torque limiter are loosened. Notice that with the left hand, we hold the Bristol wrench, which is in one of the set screws of the torque limiter. We are actually doing two things in one. We keep our hand on the wrench, exerting pressure on the tool from left to right for the purpose of moving the torque limiter hub to the right as soon as it becomes free enough to move. With the screwdriver in the right hand, we turn the torque limiter hub top to the rear, so that in the process we tend to distend or widen the diameter of the spring. The result is that at the moment in which it is possible to slip the hub against the torque limiter arbor, the hub will slip sideways, since the pressure from left to right on the Bristol wrench is waiting for a chance to be used. Only after this has been done can you be sure that the carrier return clutch spring, or the torque limiter spring, will not be sucked into the space between the arbors. The same principles which were used for the adjustments of the carrier return and torque limiter clutches apply to the tabulation governor spring. First, we must check the engagement between the teeth of the tabulation drum and the governor pinion gear. Once that position has been determined, we tighten the collar on the right of the governor pinion gear. Then we must again make the friction clutch slip while holding the hub on the left side towards the right. In this case, however, we must either turn the spring top to the rear by applying slight pressure to the right end of the spring, or top to the front by applying slight pressure to the left end of the spring, in order to make the clutch slip and to make the hub move to the right. The operational cam assembly is probably the easiest assembly to reinstall on the operational shaft. In order to preliminarily set the assembly on the shaft, we may use either the tracking marks on the cam follower, if there are any, or the lateral position of the check pawls, which will always be there. The final position of the operational cam assembly must be checked with respect to these clutch latches, or clutch release arms, as we explained earlier. Since you have to produce a good and solid engagement on 4 different points, 1 latch and 1 check pawl for each operational cam clutch, you might end up having to form one or both of the latches and/or the check pawls. This is particularly true of the 11-inch machine, which requires that the operational cam assembly be placed right next to the operational shaft, bearing in order to minimize the end play of the operational shaft. Reconnect the escapement link. All you have to observe at this point is that the link should not have any end play, front to rear or rear to front motion, without also moving the bridge to which it is attached. The cam follower at the front is bound to move with the link whenever we move it, because at the front, the link fits into a round hole on the cam follower. But at the rear, the link goes into a slot on the escapement trigger supporting bridge. In order to reassemble the print shaft, make sure that the cycle shaft, located to the left of the operational shaft, is rotated first and then rotated backwards. Top to the front as far as it will go, then top to the rear as far as it will go. It will soon be stopped by this check pawl. Then engage the print shaft with the rest of the gear train on the left of the machine in such a manner that the groove on the print shaft, yellow pencil, is lined up with the back of the screw indicated by the red pencil. Then simply reinstall the keeper for the print shaft. More about the cycle shaft is covered in Learning Program number 10, 1B. Don't forget to reinstall the bias spring for the torque limiter clutch. Then perform a functional check on all of the mechanisms with which we worked. They were the shift, the indexing, the carrier return engagement, the backspace, the spacebar, the tabulation, and the carrier return mechanism. The operational shaft should rotate feeling very smooth and easy to turn when there isn't any load on it. Before we reinstall the motor, we have to perform one more test, and that is the test of the torque limiter. We depress the carrier return key and prevent the carrier from returning all the way with our hand. When the carrier is almost all the way to the left side against the margin stops, which it will have to move in order to disengage the carrier return mechanism, then we let go of the carrier and we check whether the torque limiter has enough torque to complete the operation. We will repeat this when we study the carrier return mechanism. To ensure that all of the keylever restoring springs are properly positioned, we suggest that you use a screwdriver as shown and push it up sideways. This way, most of the springs will be properly repositioned in one stroke. At this point, you should go back to the adjustment sequence we covered earlier in order to take notes on the adjustments discussed. Only then should you perform the adjustments on your machine. While making the adjustments, you should refer to your notes as much as possible, in a deliberate effort to determine whether or not you can work with them. Upon concluding this program, you should continue this portion of the IBM Selectric Typewriter training with our learning program number 10-1B, entitled Cycle Clutch or Print Clutch. The print clutch is the last and also the most elaborate source of positive power for the IBM Selectric Typewriter. Thank you for staying with us all the way to the end of this package.